Hey everybody, it's Ripley again. We are in 4.6, optimization problems, or as I like to call it, max-min madness. All right. Hopefully you guys all remember the question or the problem from Algebra 2. You've seen it before. Remember this guy? A farmer has 1,000 feet of fencing to build a try again, a pen, and it's going to be, what kind of pen? It's going to be a rectangular pen. A rectangular pen along the side of a barn. Thus using one side. Draw a picture here in a sec. I know you've seen this. It's alongside of a barn, it's alongside of a river, there's always something. All right, what are the dimensions that maximize the area of the pen? And what is that area? Now this is really two separate questions, but we'll be able to answer it all at the same time. Okay, so I'm going to put a set of rules over here, and I'm going to put them in blue. We're going to do it one thing at a time. All right, so these are the max, min, Ripley's rules. So Rip's rules. All right, nothing to it. First things first, always, number one, draw a picture if you can. Draw a pic if possible. That's always the first rule. Okay, so what's really going on over here? We'll change color pens. All right, we've seen this, right? So here's my barn, and then my rectangular pen is going to steal a side of the barn. Okay? Nothing to it. All right. Now, part two. Now, this is the most important, too. I'm going to put an asterisk here and a rainbow over the top of it so that we know this is the most important thing. Ask yourself, literally ask yourself, what is being maximized or minimized? That's the most important question. So I read the problem again. A farmer has 1,000 feet of fencing, okay, nothing so far. What are the dimensions? Ooh, that max area. Okay, so in this case, let's change colors again. This is going to get old, but that's all right. Area. So I'm going to write A as an area. Okay, now part three. Oh, wow, I am going to have to. Now, trust me, if you can answer this question every time correctly, half of your work is done. Part three, write an equation to represent question two. Well, what is area? What's the area of a rectangle? It's base times height, but we're mathematicians, so we're going to use some notation here. All right, so we're going to have an x, and we're going to have a y, right? So the area of that rectangle, which I'm trying to maximize, is equal to x times y. Okay, now I'm going to do a little parenthetical deal over here. We're going to do a little indent right here. All right, here's my indentation. This is usually not a function of one variable. And that presents a problem, right? Calculus is real valued functions of a real variable, but the problem is area is a function of both x and y. Now you may already be going, Ripley, we did this in Algebra 2. Why are we doing it again? Trust me, with calculus, it is so much easier. Now that brings me oh so gently to find what I refer to as a shoehorn equation to convert part 3 into a function. Into a function. I can't write f of x because in this case it's going to be either a of x or a of y of one variable. Now, again, if I read through the problem, a farmer has 1,000 feet of fencing. That's a piece of information that I can use, right? I mean, if I think about 1,000 feet of fencing, all right, so that tells me that this side plus this side plus this side is a total of 1,000. So it appears that my shoehorn is actually x plus 2y, which is equal to not the whole perimeter, but the amount of fencing that he has, is 1,000. Now, what do I mean by find the shoehorn so that I can convert this guy into a function of one variable? Well, I just solve for one of the variables. Nothing to it, right? What's the easiest one to solve for? Hey, let's solve for x, make x go away, right? Because now I can just substitute this guy in for x. And watch what happens. Area becomes, well, 1,000 minus 2y times y, right? So now I have area as a function of y equals negative 2y squared plus 1,000y. Piece of cake. Now, remember back in the day, remember back in Algebra 2, when we didn't have calculus, we looked at this thing and we said, okay, it's a parabola. The area as a function of y could be expressed as a parabola, and that parabola opens down. So I have a max value here. Guess what? Those days have come and gone. Now what we're going to do is we are going to use calculus, i.e. derivatives, to prove the existence of maxes and mins. Watch. All right, let me change. This is a pain in the butt. All right, I've got area as a function of one variable. I'm going to find out where that function is maximized. How do I do that? I take a derivative. Remember how we had to do it over here? When we had a parabola, we had to go, okay, x equals negative b over 2a, and then I have to go f of negative b. Remember all that garbage? And we had to memorize this formula. Even though we proved it, we showed it, we had to memorize this. Those days are gone. Look, negative 4y plus 1,000 equals 0. In a puff of algebra, if I want to solve this, right? I mean, it's relatively easy to see if I set this equal to 0. I get that y equals 250. True? I mean, the negative 4 times 250 is negative 1,000. Negative 1,000 plus 1,000 is 0. Oh, wait, now don't get cocky. Let's be real careful. We still have to prove that this thing is a max. Remember right here, prove that there's a max or a min. So I know that I have a critical point at y equals 250, correct? Sorry, I'm getting smushed in on here. So 250. Find a value to the left. Now, this is always very helpful as well. Notice that we turn a into a function of y. So what values of y make sense? Well, can y be 0? If y is 0, let's change colors because this is kind of fun to do. If y is 0, doesn't that mean that x lays right up against the barn? You better have some real skinny cows. Similarly, if y, that would be for y equals 0, right? What would happen if y equaled 500? Which theoretically is the biggest that y could be, true? Because if y is any bigger than 500, I'm not going to be able to enclose anything. Well, then I'm going to have a fence that comes way out here that's 500 on each side. Again, you better have real skinny cows, correct? So, theoretically, and you don't have to put this on, but it really helps. I mean, y is a dimension, and we're not talking about Star Trek land here, so we know that the smallest that it can be is 0. We also could say that the biggest that it's going to be is 500, although we don't really have to worry about that because there are no other critical points. They would have shown up. Now, what do? The name of the Ripley-Doodle diagram is a primed y. Let's plug values into the derivative, right? If I stick 100 into here, what do I get? I get a positive. If I stick 400 into here, what do I get? I get a negative. So guess what? I know that the shape of this curve right here is going to be up, level, down. I have a max. Wonderful. Okay? And then, of course, always, 6, whoops, wrong color. Sorry, I need to be consistent. You guys know me. Yeah, right. I have all these different colored dots all over my paper. That's pretty funny. Last but not least, make sure to answer the question. The question that is asked. Okay? So I'm going to bring this thing over here now. So let me change colors back to black. And that's really it. Those 6 little rules will make you be very, very successful. By the way, believe it or not, excuse me, there's no more instruction out of this section. This is it. This is all that you have to watch. When we get in class, we're spending a lot of time in this section because it's really, really important. It really sort of strikes at the heart of why differential calculus is so important and so useful. All right, so where were we? I know that y equals 250 is where the max takes place, but let's make sure. It says, what are the dimensions? So that implies I know that a max of area occurs when y equals 250. Problem is, that's not the dimensions. I need to know what x equals. Now this is the beauty of setting up your shoehorn equation perfectly. That should be an x. Notice that it's already set up for me, isn't it? It's tailor-made for me to solve for x. So I know that x equals 1,000 minus 2 times 250, which is affectionately known as 500. Now I have the dimensions. X equals 500. Y equals 250. If I wanted to be fancy, I could say it's 250 by 500. I have answered that part of the question. Now, wait, there. And what is that area? Well, now I've got 19,000 different things that I can use. Not really 19,000, I have 2. I can either simply say that the area is equal to, since I know the dimensions, I can go 250 times 500, right? Which is, I don't know what the heck that is. What is that, 12,500, right? 12,005, right? 1, 2, 3. Oh, no, it's 125,000 square feet, isn't it? Too many zeros. 1, 2, 3, 4, yeah, 5, 1, 5, yeah, okay, sorry, I've got commas floating around. Or, if you got a little more savvy, and sometimes it's just straight up easier, can't I simply plug y equals 250 into the function that I already worked so hard to make? A of 250 is equal to negative 2 times 250 squared plus 1,000 times 250. And I'm going to get the same answer. All right? You know what? I'm not even going to go, well, what the heck? Let's go over. Why do I have a calculator if I'm not going to use it, right? So I can quit. If I go clear, let's clear. Remember that? That was a good time. So 250 times 500. Always double check, especially when I'm doing mental math. Look at that, 125,000. Now let's double check. Negative 2 times 250 squared, right? Plus 1,000 times 250. Let's see what I get. Oh, look at that. Isn't that awesome? All right, so these 6 rules are going to help you so much. The most important rule, no doubt about it, is ask yourself, what am I maximizing and minimizing? What am I maximizing and minimizing? Where do I start this problem? Once I've answered this question right here, notice the rest falls out. Find an equation, all right? And find a shoehorn to turn it into a function. Use calculus, answer problems. Nothing to it, all right? Easy peasy. What did I just do? That's funny. All right, easy peasy. Hit the wrong button. Nothing to it. Like I said, we're going to spend like 4 days on this in class. We're going to be doing a ton of this. It really is important. So thanks for your time and attention, and I'll see you in class tomorrow. Bye-bye.